Okay, so next let's talk about another important factor considered in the Garph-Bert model, which is called the positional embeddings. So according to the previous part, when we do the sampling of the subgraphs, we mentioned that we discard all the edges among the nodes in the subgraphs, right? The main reason we discard these edges in the subgraph is because we plan to learn this Garph-Bert for parallel learning instead. Then, if we discard this connection among the nodes, then we may discard some of the information, right? So to complement this kind of discarded edge information, we try to incorporate the position information of the nodes in the graph instead to capture the structure information of the nodes in the graph. It is the reason why you need to first consider the positional embeddings for the nodes in the graph. And how can we learn the embedding vectors for the nodes? The formula given a subgraph. Now, if we have this one as a target node, and all the remaining nodes are the surrounding neighborhood, which define the learning context actually. And so together we define one subgraph with some from the previous part, right? So by fitting the subgraph into this initial embedding component, we can learn the initial embeddings, which will be serving as inputs for the foreign encoders of the transformers. So given this subgraph, we have both the target node as well as surrounding context of the target node, which are these three nodes that we define here, right? So we define the initial embeddings for all the nodes. We have inputs. It covers 4 parts. We have both the row feature embeddings, because for each node in the graph, we also have the row embeddings, right? So we try to capture the row features as inputs for learning the embeddings. Therefore, we have one node row feature embedding vector as shown here. We can learn the row feature embeddings via some pre-trained models, depending on the modernity of the feature we have for the nodes. Now here for node Vj, we can define its row feature as xj as we show here, right? Depending on this xj can be either an image, it can be text, it can be some numbers, right? And we can define one corresponding embedding function as we show here. Now if this xj is an image, we can define this embedding as a CEM model to compress them into an embedding vector like ej as shown here, right? If this xj is text, then we can define the embedding function as a LSTM or BERT for compress them into the embedding vectors. If this xj is some numbers, also row features, then we can define the embedding function with MLP for compress them into embedding vectors, like ej as shown here, right? So this ej can capture the row feature information for the nodes in the inputs. As we show here, besides the row feature embeddings, we also have some other positional embeddings to capture the positional information for the nodes in the graph. We define 3 different positional embeddings covering both the WL absolute positional embedding, intimacy-based relative embedding, as well as hop-based relative embeddings of the position information. And how can we define them? Let's talk about this WL code-based absolute position embeddings. What is WL? So WL actually is short for the wise final domain. Is algorithm. This algorithm can calculate a code for each node in the graph based on its position information in the graph. So we provide with this WL algorithm at the bottom part. I'm not sure if you have heard about this algorithm before or not. This algorithm is very important for graph learning. So the WL algorithm tries to assign each node with an index code to denote its position in the graph. So for the nodes with the same position, they will have the same WL code instead. What do we mean by the same position? The same position means if we switch to position of 2 nodes in the graph, then the graph structure will not be changed. In other words, before we switch the position of 2 nodes and after we do the switch, the graph structure will remain the same. Then we can say the 2 nodes have the same position. And at the bottom part, I will show you with an illustration about this WL algorithm and also based on a toy graph dataset inputs. Let's assume if we have one graph input, like something like this one. We have like 6 different nodes, right? We will find that we have 2 nodes that have the same position. Now this is A node and B node as we show here, right? We find this A node is connected to 2 nodes, this one and this one. And the B node is also connected to these 2 nodes as well in the graph structure, right? Therefore, we can see if we switch the position of A and B, the graph structure will remain the same, right? So according to the graph structure, we only have one single pair of these 2 nodes, they have the same position. All of the remaining nodes on the pairs, we have different position state, right? And then how can we calculate the WL code for the node based on the algorithm? So the WL algorithm works in an iterative way by assigning the nodes with some codes iteratively. So given one graph input like this one, we can assign them with some initial codes for each node. Now here we assign them each with the value 1 as a code, right? Because this is the initial code for all the nodes. We assign them with the same code at the very beginning. Then the WL algorithm will do the aggregation of the neighborhood information to redefine the codes. And how can we do the aggregation? If we take this node A as an example, this node connects to two nodes, right? This one and this one. Both of them, they have a code 1 as we show here, right? Therefore, by aggregating these two nodes into the node A, we can redefine its new code in another way, right? We can define this A's code as 1, 1, 1. What is the 1 before the comma? The 1 before the comma denotes its original code we have for A, right? Its original code is 1 as well, right? Therefore, we have 1 comma here. We have 1, 1 as we show here, right? Therefore, this 2, 1 denoting the 1 we aggregated from the neighbors of these nodes, right? And in a similar way, we can also aggregate the neighbors nodes to redefine the B's code as well, because this B node is also connected to these two nodes 1, 1, right? Therefore, we also redefine the B's code as 1, 1, 1, as shown here. Similar for the other nodes. Now for this one, it connects to 2, 3 nodes, all have the node 1 as we show here, right? Therefore, we define its new code to be 1, 1, 1, as we show here, right? So normally the code, we have after comma, they are ordered according to the values of they are sorted, from lower one to high ones. Since they are all ones here, then we don't need to differentiate them from each other. They are all the ones that we show here, right? So by aggregating the neighbors code, we can redefine the new code as is shown in this one, right? So compared with the original code, this one is more similar to a string actually, right? Because originally we have integers as a code. Then by aggregating them together with commas, we define a new string as a code for the nodes. So given the string, we can further project them to some integers as well by some hash functions, right? So therefore, we have step 2. We project each of the string to an integer via one hash function. So for the strings with the same value, they will be projected to the same integers as the new code instead. So in this way, we can redefine a new code for the nodes based on their strings, right? So that's this one will be projected to one integer according to the hash function into a 1 instead, and this one will be projected to a 2 as the code. And since they all have the same strings, they will be projected to a 2 as the code. And this one is more complex; it will be projected to the 3 as the code instead according to the hash function. So this is a new code we have with one iteration, right, for updating. And furthermore, we can further aggregate the neighbors code again and to redefine the new string code as shown here, right? If we still take this A as an example, right? So since its original code is 2, and it is connected to two nodes 2 and 3, and we can define its code as 2, 2, 3 as we show here, right? Similar for the others. Then furthermore, based on this new string, code, we can further project them to integers via the hash function again, right? So we can have a new code for all the nodes in the graph. And this process will continue until convergence. If we have the code remain the same in the 2 iterations, then we can achieve the convergence. Now here we have achieved convergence already for this toy example. And in the convergence case, then we can have assign all the nodes with one unique IDs. And for the nodes with the same position, then we have a same ID as output instead. Now here for the nodes A and B, they will be assigned with one unique ID, which is 4 as we show here. And they have the same code as output. And for the remaining nodes, they have different positions, therefore they will be assigned with different codes by the WLA algorithm. Okay, so this is the WLA algorithm we can use for define the codes for the nodes in the graph. And based on this WL code for all the nodes, we can further define their position embeddings by fitting them into the position embedding function as we defined before. We have defined one similar function for the transformer. If you still remember in the paper, for the transformer paper, right? So given an integer input, we can project this integer to an embedding vector, right? With both the sine and cosine function we define here. And we can apply a similar function for define the position embedding for nodes based on their WL code. Now, if we denote this Vj as the WL code for the Vj in the graph, we can define the corresponding embedding vector as Ej as we show here by utilizing both the sine and cosine functions. Okay, so this is the way we can define the position embedding based on WL code of the nodes. Besides WL code, we also incorporate some other position information of the nodes in the graph to define their position embedding as well. Now here we can define one corresponding position embedding vector based on the intermediate score among nodes as well. Similarly, we can also define the distance based on hops among nodes to define its position embedding vector as well, as we show here. So by defining different position embedding together with the raw feature embeddings, we can sum them together for define the raw embedding vector inputs for the encoder to be defined to be introduced later. So we will sum all of them together, and the result will be serving as input for the encoders. So this part is for the initial embedding. So this initial embedding can capture both the raw features as well as the position information in the graph inputs, right?